In the previous video, we saw the aggregation and transformation math in formula form. I find it easier to understand this math in matrix form, and that's what we'll take a look at in this video. Consider this particular graph with 5 nodes. Now every node is connected to a number of other nodes, and each node has a set of features. Imagine that you're representing these node features using a feature vector. So we have this feature vector associated with each node in your graph. Now, the interconnections between the nodes in your graph you represent using an adjacency matrix. The adjacency matrix contains as many rows and columns as the number of nodes in your graph. And for every connection that exists between pairs of nodes, the adjacency matrix contains a 1 in the corresponding cell. Cells which have 0 indicate no connection between that pair of nodes. When you perform the aggregation and transformation to generate node embeddings, you work with embeddings and features in matrix form, and this makes the mathematical formulation very easy. For example, this is how you'd represent the node features of all 5 nodes in matrix form. The feature vector for each node has 4 elements, and there are a total of 5 nodes in our graph. This is what the matrix representation of the node features look like. The dimensionality of this node feature matrix is 5 by 4 because we have 5 nodes and 4 features for each node. In order to transform these node features to generate embeddings, these node features are passed through a neural network layer. The neural network layer is just a learnable weight matrix. Observe that I've set the dimensionality of this learnable weight matrix to be 4 by 8. 4 here represents the input channels of the neural network layer. 8 here represents the hidden channels, that is the number of hidden units in the neural network. We know that the node features matrix is 5 by 4 and the learnable weight matrix is 4 by 8. So this is a simple matrix multiplication operation. In this example, when our node features are passed through the neural network layer, each node will be represented by an embedding of dimensionality 8. So the output in embeddings for each node will be 5 by 8, 5 nodes embedding dimensionality 8. Now, how does this transformation relate to the formula that we looked at for aggregation and transformation? Here is the simplified formula. This learnable weight matrix that you see on the right corresponds to WL that you see here in the formula. Passing the node features through a learnable weight matrix generates embeddings for each node. And here I represent each embedding using H1 star, H2 star, and H3 star. In this way, you'll have embeddings for all nodes in your graph structure. In order to update the embedding representation for each node, you need to perform aggregation, and this aggregation performed using an adjacency matrix to figure out who the neighbors are for each node. To update the embeddings for a particular node, you only consider nodes that are connected to that node. That information is contained in the adjacency matrix. To generate the embeddings for each node at the output of the next layer, you have to consider the node itself, which is why the adjacency matrix that you use to aggregate the embeddings from the neighboring nodes should contain a self loop. That is, every node should be connected to itself. In this way, the aggregation operation will consider the embeddings of the neighboring nodes as well as the embedding of the current node to find the embeddings of the current node at the output of the next layer. And of course, in order to capture the non-linearity in the node embeddings, we apply an activation function to get the updated embeddings for each node. Thus, we perform the transformation, aggregation, and the activation function to get the final node embedding. And here we've considered just one layer with number of hidden units equal to 8. So the final node embedding will be a matrix of 5 by 8,